What I want to look at here is I'm going to discuss proof by induction. Now this is a method that is very important at the advanced higher level and beyond, and is something we need to make sure we get our head round. So I'm going to tell you exactly what it is, what the premise of it is, how to solve it, and then show you a couple of examples of using it, and how straightforward it actually is to implement in order to solve a conjecture. Now, proof by induction provides a framework for proving conjectures which have a basis surrounding positive integers. Now, they link a scenario with a given pattern where we involve the nth term in the conjecture and base our proof around this. So what we do is we have a conjecture which emits some sort of pattern, and it gives us some sort of sequential-esque theorem. And what we do is we use the nth term within that to prove by induction, and using the principle of induction, that it is valid throughout for every value it can take. Now it's a lot to throw at you, but one thing I want you to remember is that this principle of induction follows three key steps. The first step is that we make a general statement about n, which belongs to the group of integers z, and we can demonstrate it to be true for some value n equals a. Now generally this is the first term that it is valid for. So for example, if we were given a conjecture and it said n is greater than or equal to 1, we'd look for the value n equals 1 and prove it to be true for that term. It's then assumed it holds for the term n equals k, and is shown it holds for subsequential terms n equals k plus 1. So once we've shown it's valid for a term, we then assume it's valid for any generic term, and then we use that and we prove that it is valid for the next term in the sequence. So what we can then do is draw a conclusion from it, that since it's true for some n equals a, and it's true for a generic term, then it's true for the subsequential terms that follow it, so n equals a plus 1, n equals a plus 2, etc. And therefore, by induction, it's true for all n belonging to the integer values, so n equals 1, 2, 3, etc. Now, it's a lot of information there to throw at you, but the key thing is those three steps to solving it. And just base it around the fact you prove it for the first, you assume it for any, you prove it for the next, you write your conclusion, and you state what it means. Now, the easiest way to show this in action is by showing you a couple of examples, which I'm going to do now. So let's imagine I want to prove by induction that Cn equals a half n bracket n minus 1 when Cn plus 1 is given by Cn plus n. And I'm telling you that C1, the first term, is equal to 0, and n belongs to all the integer values. So n is always an integer value. So what we have to do is, first step, is we prove that it holds for some generic term. Now we're told that C1 is equal to 0. So if C1 is equal to 0, what we want to do is prove that it holds for C2. If we can show that it holds for C2, both of these conjectures, then it is true for a set term. So let's imagine I'm going to look at this first. So using this format, I know that C2 is equal to a half times n, which is 2, bracket 2 minus 1. So that's equal to a half times 2, which is 1, times 2 minus 1, which is 1. So my term C2 is equal to 1. If I then use this format here, I've got C2, which is equal to Cn, which in this case is C1, which is 0, plus n. Now n plus 1 is 2, so the next term is 2, which means that n is 1, so it's equal to 0 plus 1, which in this case is equal to 1. So then it holds for a specific term, C2. What we then say is fine, so we assume that it's true, or that it holds for n equal to k. So in that case, what that means is that ck is equal to a half k bracket k minus 1, And what that then means as well is that c of k plus 1 is equal to ck plus the k. What I then want to do is now look at when n is equal to k plus 1. So if I can then prove that it's true for k plus 1, I can then prove it's true for anything. So ck equals a half k bracket k minus 1. So what I'm going to do is say that therefore c of k plus 1, that's equal to a half bracket k plus 1 times k plus 1 minus 1, which if I then do that there, that'll then give me a half k bracket k plus 1. So that's ck plus 1, that's my next term there. And if I then look at this here, my ck plus 1, for this case, that would be given by a half k bracket k minus 1 plus k. What I'm going to do is take out k as a common factor here, and I'm going to get k times a half k minus a half plus 1. So that's then going to equal k bracket a half k. It's going to then be minus a half plus 1. So that's going to be plus a half, which is equal to a half k bracket k plus 1. So what that then means is that both of these match. So because both of these match, it is now true for the next term in the sequence. So it's true for a k plus 1. So what I can then say is therefore since it holds for n equal to 1, so that gives me c1, and n equal to k, and n equal to k plus 1, it's therefore true for all n belonging to z. So for all n belonging to my group of integer values. So what we've done is proven it is true for everything by induction, and it's using those 3 steps. Prove it for a specific value, in this case I'm going for my c1. Assume it's true for k, show it's true for k plus 1, and then what you've done is shown it's true for a specific one, which has been taken as being generic, so it then holds for the next term in the sequence, so it's going to be true for any value of n that we pick, regardless of where it is in the sequence. So we've proven that by induction. And we have to make some sort of statement here at the end that links everything. So we have to make some sort of statement saying that it holds for whatever the specific term is, and we know it holds then for n equal to k. We've then shown it works for n equals k plus 1, so then it has to be true for all n. Our statement at the end has to revolve around that somehow, and we have to get all these factors involved for the induction process to be complete. Another example for you, I want to prove by induction that 2 to the power of n is greater than n for all n belonging to the set of natural numbers. So what I'm going to do is I'm going to follow the same set of steps. So I want to prove it for a term. Now in this case, what I'm going to do is take n equal to 1, because that is the lowest number within our natural set of numbers, and I'm going to show it holds for that. So what that then means is I've got 2 to the power of 1, which is equal to 2, and that is then greater than 1. So this here holds for n equal to 1. What I'm then going to do is I'm going to assume it holds for n equal to k, i.e. 2 to the k is greater than k. What I'm then going to say is we're going to look at n equals k plus 1. So I'm going to have 2 to the k plus 1 is greater than k plus 1. That's what I want to prove. So 2 to the k plus 1 is greater than that. Well, if I split this up here, what that then means is 2 times 2 to the k has to be greater than k plus 1 in order for it to hold. Now we know this conjecture here is true, so 2 to the k is greater than k, which means that this holds because this is greater than that term there. And because we're multiplying it by 2, what that means is even if we add 1 on, we're going to be doubling the value here every single time. And doubling that value as k increases in size is going to be more than adding a single value on. So what that then means is that I know my conjecture of 2 to the k plus 1 is always going to be bigger than k plus 1 for all values of k. Then I have to write my final statement. So what I know is that since it holds for n equal to 1, n equal to k, and n equal to k plus 1, that implies it holds for all n belonging to a set of natural numbers. So again, we've proven it by induction from that. We've shown that it holds for a single term, so our starter term there. We've assumed it holds for a generic term. We've shown it works for the next term. And then we know that's going to be there. And again, it comes from knowing that we've got a truth prior to it. So we know that 2 to the k is bigger than this k here. So because we know that to be true, we've assumed it here. What that means is we can then use that assumption as part of our proof. Okay, so we can assume that from there. So proof by induction, it's a set technique. It follows those 3 steps, and if you can remember them, regardless of what the question is like, you'll be successful throughout. You just have to remember, prove for the first, assume for the k, show for the k plus 1, and then the most important part, beyond the mathematics, communicate your answer clearly and state what it means.